presentation. I'm very happy to be here. Okay. So today I will talk about something related in my title, so Topological Recursion and Resurgence and BPS structure. So basically, this is some joint work, based on some joint work with several people. The first one is with Koike and Yumiko Takei, and the second one is with Omar, and also third one is with Marcos Marini, and the last one too. I hope to put it in academia until the end of this year with Brian and friends. Okay. Okay. So let me explain my motivation first. So basically, my talk is based on some analysis of the topological recursion partition function, its relation to the tau function. So as Bertrand explained yesterday, so topological recursion is a kind of some machinery or some recursion relation, so which is some analog of free energies and correlators from a given spectral curve, so which is denoted by sigma, and it is assumed to be some rational function of x and y. So it defines some algebraic curve. And so it is also, maybe most of you know it is related to the enumerative invariance and also integrable systems through some quantum curves. And also it computes some knot type of invariance. So it is interesting because it's related to very many topics. And main question I want to discuss in my talk is some resurgence property, or some stock structure of this topological recursion partition function. So as you may know, so if we consider some generating series of these free energies, so usually this free energy diverges. This becomes like 2g to the factorial as Ricardo explained. So we need to take some Borel summation and so on. Due to the divergence, some Stokes phenomena will happen, and we want to understand the structure. So all of my talk is, first of all, I will give some explicit and exactly solvable examples, which is coming from some hypergeometric ODEs, and they are corresponding to some class of genus cell spectral curves. And also, the formula is actually very related to the BPS structure, which was discussed, not to discuss, but sorry, joint structure is very related to the BPS structure. Okay, and also, in the final part, I will discuss some genus one spectral curve, and using some relation to the Van de Waal tau functions, I will discuss some conjecture on the area derivative of the partition function proposed by Gu and Marini in last year. So first I will talk about some explicitly or exactly solvable examples coming from hypergeometric ODEs. Let me start some very easy examples, fundamental examples, which is a spectral curve of the Gaussian matrix model. But actually, so in my mind, so I always try to understand topological recursion by using some relation to the WKB and some special functions by quantum curves. So actually, so this is the classical limit of the Weber equation. So let me allow to call this curve a Weber curve or Weber spectral curve. And it is a parabola, so y squared equals x to the power 2, and also it contains some non-zero complex number. Okay. So if you run the topological recursion, so it is known that so this computes some Euler characteristic of the moduli space of genus G Riemann surfaces. And it is written by Bernoulli number. And as you see, so since Bernoulli number grows like this, so this has zero radius convergence for any fixed parameter nu. So it has so it is divergent series in algebra. So we can discuss about summation of that. And fortunately, so in this example, so we can analyze the structure explicitly because of the explicit formula by Bernoulli number. So I forgot to write down the definition of the Bernoulli number, but if you know the definition of the Bernoulli number, so you can easily compute the Borel transform. So Bernoulli number is basically some series coefficient of this, something in the exponential in the denominator. So zeta is the Borel Laplace dual variable with respect to h bar. Okay. And you see, so this one, so the Borel transform is defined as a germ which converges around the origin, but this has some analytic continuation. So this is the expression of the analytic continuation. And then you see, so it has a singularity at this point, coming from the zero of the denominator. So it has some periodic form. And so if this Borel singularity appears on a positive real axis, then we cannot define the Borel sum. So some Stokes phenomenon should happen. But okay, so okay, so when the this parameter new has a non-zero real part, then so this delta has a non-zero imaginary part, so it doesn't lie on the real axis, so we can take the border. But depending on the imaginary part depending on the real part of this new, so we have some different expression of the Borel sum. So actually, so you can find some integral representation of band G function in Wikipedia, and this is a formula. So you don't need to care about some terms. So essential part is given by band G function. The previous Bernoulli series can be regarded as some Stirling expansion of this kind of band G function. Okay, actually, so this continuous change of the expression is nothing but a Stokes phenomenon, which is caused by the Borel singularity. So when real part new is zero, then this appears on the singular Laplace integration contour, and the difference of that guy is computed by so-called alien derivative, so which is also discussed by Ricardo Stokes. So in his talk, he discussed some logarithmic branching singularities, but if it has a pole, then the alien derivative is just simply taken by and so on. So after some computation, so you have this formula, and this appears on maybe I have so this alien derivative basically so this is the information of the Stokes jump. So when real part of nu equals 0, then some singularity appears in this way, and the alien derivative is Stokes automorphism relates the Borel summation in these two directions, and these differences are given by the residues, and which is nothing but the alien derivative. And after summing over the residues, so you have some explicit action of the Stokes automorphism. And in the case, so since you have seen k square in the denominator, so you have some dialogue and so on. Yeah. And actually, so this computation was already done by Packbeck Skepper. Okay. So this is very explicitly solvable. And actually, so you can understand this appearance of dialogue as some reflection formula of these band G functions. Okay. So actually, so this is an example of the Weber equation, but actually, so this kind of example can be obtained by some class of genus zero spectral curves, which is coming from some hypergeometric differential equation. So for example, so this is the classical limit of the hypergeometric equation. By the way, so this is basically the result of Yumiko Takei's master thesis. So anyway, so we can apply the topological recursion for this genus zero spectral curve. And here, so this nu zero, nu one, nu infinity is some parameter attached to the singular point of this spectral curve. So basically, so nu zero is a residue of y dx at the origin up to sign and so on. And then you can, if you run the topological recursion, so you have this expression. So here, so you see, so the free energies are written by some linear combination or some superposition of the previous Gauss, Weber free energies with some appropriate coefficients. Yeah. Actually, so we can prove the formula by using some relation between WKT and topological recursion and so on. So basically, this is a consequence of the quantum curve. Actually, so since the quantum curve relates WGN or omega GN of the topological recursion and WKT solution, and using the relation, so we can derive some relation between free energy and coefficient, so-called, of the quantum curve. And quantum curve in this case is nothing but a Gauss hypergeometric differential equation. And actually, the symbol of the quantum curve or differential equation is known to be related to some Stokes data or monodromy data of the quantum curve. And for Gauss hypergeometric equation, so it is known that such a monodromy is written by some monodromy or some connection matrices are written by some gamma functions. So we can understand this as some Stirling expansion of the gamma function. So in the end, so we can obtain this kind of formula. So in some sense, so this is some kind of special function theoretic proof of the formula. Okay. And actually, so this is the case of hypergeometric differential equation, but maybe you know, so there are several several equations obtained by confluence. So for example, Kummer's equation or Bessel's equation, Whittaker, Legendre. So there are many examples, but we can obtain the similar expression for each member. And also, since this is just a linear combination of the previous free energy, which was exactly probable so consequently, so we can understand the resurgence structure. And actually, so this is a list of the other examples coming from the confluence of the previous one. So maybe it's too small, so maybe you can check your, maybe Neji already sent my slide to you, so if you want to check the formula, so please look at it. Anyway, so the point is, so everything is written by some appropriate linear combination of free energy of the previous Weber's one, with certain weight. For example, here 2 or minus 1 is appearing, and some number appearing with the denominator is slightly different, depending on the model. Actually, so there is one way to describe some universal formula of these examples, and to describe such a to give such a formula, so it is convenient to recall the notion of the BPS structure.
Okay. So I could see that there were Bernoulli number appearing for all of them on
yes.
that list. Is it coming from the fact that you've got the same structure of poles in the Borel plane, or
could you say that?
is it coming? Where is it coming from? From the structure of poles in the Borel plane?
In the proof, I didn't use so this Bernoulli number is similar, yeah. So consequence of some. So for example, in Bessel's case, for example, it is known that some Bessel's connection formula from origin to infinity, for example, is written by gamma functions. And so it has some Bernoulli number as a starting expansion, and using this arrow, so we can obtain the formula. So we use some quantum curve and the WKB theoretic computation of the Stokes data. Am I answering to the question? Or later we can discuss. Yeah, anyway, so once we have this kind of expression, then we can understand the Borel singularities perfectly. Okay. And actually, so maybe I should say, so for example, if you look at this term, for example, F1 is written by some product of 4 plus 3 factors. So you have some 7 factors in logarithm in F1. And also Fg is written by some 4 terms, linear combination of some 4 terms. And actually, so in total, you have some 7 terms. And actually, so this 7 is corresponding to the number of the degeneration in the Stokes graph. So I omitted the definition of the Stokes graph, but actually, so the previous spectral curve, so right-hand side of the spectral curve can be regarded as some quadratic differential, and you can describe some trajectories from 0 to pi. So maybe it's better to recall. Basically, the trajectory or Stokes graph is defined by some flow defined by like this. And usually the Stokes graph is the trajectory attached to some ramification point. But usually this Stokes graph is used to define test of the Borel summability as a H bar series. So it should contain some information of the arguments of the H bar. And the phase of the Stokes graph is the parameter theta appearing here. And you can look at the Stokes graph from theta equals 0 to pi. Then if you do that from 0 to pi for hypergeometric example, so you observe exactly 7 degenerations. And 3 of them are kind of loop type. So this is, so blue one is the origin. So origin and 1, so it is a regular singular point. And also infinity is a regular singular point of the hypergeometric equation. So it is order 2 pole in the quadratic differential. So around such a double pole, so sometimes this kind of loop type of degeneration. So this is also some degeneration, loop type degeneration around infinity. And the other 4, this one are saddle connection. So saddle connection is appearing. Okay, so you have seen 4 saddle connections and 3 loop type degeneration. And actually, so this can be related. This is related to the previous decomposition. But to write down the formula, so I also have to introduce the notion of BPS invariant attached to such a degeneration. So this is closely related to the DT invariant in the previous talk by Tom. So basically, so in our setting, so this BPS invariant counts or weighted counting of some degeneration in the Stokes graph. But it is not attached to the saddle connection itself, rather to the cycle on the spectral curve, which is denoted by the set of cycles is denoted by term. And if it is maybe I should forgot to prepare a picture. So on Stokes graph, so sometimes as you have seen, so this kind of degeneration happens, and then you can naturally attach the cycle on a spectral curve which surrounds the saddle connection. And for such for such cycle, I assign the appropriate BPS invariant depending on the type of the degeneration. And if it is this kind of standard saddle connection, I attach +1. And if the saddle connection is loop type, then I attach -1, and so on. So I omit the precise definition, but yeah, anyway, so you can attach BPS invariant to such a degeneration. Okay, so and together with the central charge map which appeared in the previous talk, so this triplet forms a BPS structure in the sense of tone. But sorry, I don't have time to explain. But at this moment, you should, the precise axiom of a BPS structure is not important. But the consequence is the following. So once you have the set of BPS invariant coming from the Stokes graph of quadratic differential corresponding to the spectral curve, then the previous free energy is written in this compact way. So it is the sum over all lattice whose central charge lies on the upper half plane. So precisely speaking, this H is some semi-closed upper half plane. Okay? And the corresponding ones are written by this way. So its BPS invariant is appearing here. So for example, if you look at the previous formula of Gauss hypergeometric equation, so you have 4 terms with omega equal 1 and 3 terms with omega equal -1. So this is a precise decomposition based on the BPS invariant. And so these also can have the same structure. As for example, so this number 4 appearing here is related to the BPS invariant which connects the 2 simple poles. And this also appeared in Fabian Heiden's recent paper. Okay. So this is the relation between topological recursion and BPS invariance. So this is valid in genus zero spectral curves coming from hypergeometric equation. But we expect that this kind of relation can hold for more general spectral curves if the BPS structure is uncoupled. So I don't explain the meaning of uncoupledness, but basically such a BPS structure gives this kind of some superposition of Elmid Weber or some fundamental pieces. Yeah. So in coupled cases, we cannot expect such a decomposition is available. Anyway, okay. There are a couple of remarks. So thanks to the previous formula, so we can compute the alien derivative of the free energies, and then we obtain some similar expression of Pasquetti Schiappa form. And in here, so you have seen some BPS invariant. So in the resurgent analysis, so maybe Ricardo explained. So the action of the alien derivative is written by some another Franz series. So in this case, Franz series is trivial, but in front of the Franz series, so you have some so-called Stokes constant. And in our example, so the Stokes constant is realized by this BPS invariant. And maybe I don't have time to explain, but actually, I didn't explain what is the Boros coefficient, but Ricardo talked it in his talk, but he didn't define. But anyway, there is important notion of the Boros symbols, which is related to the Stokes data of the differential equation. And in our setting, so actually, the Boros symbol of the quantum curve also have some interpretation by topological recursion, as I said. So actually, so this Boros symbol is related to the free energy. And so we can also look at the Stokes structure of the Boros symbols. Then we can show that the Boros symbol satisfies this jump formula. So actually, so this also appears in Gaioto Manaiske's work. So this Boros symbol is a counterpart of the Fock-Gonchar coordinate. Yes, and so this one is sometimes called Kontsevich-Soberman operator or BPS automorphism and so on. And usually the BPS invariant should appear in the power of the automorphism. And actually, so the previous definition of omega, so for example, as I said, so omega equal 4 is special degeneration, but so this definition was given by looking at the Stokes structure of symbols, but I was lucky so because it is also realized by actual Gauge invariant by Fabian Heiden. Anyway, so this is another remark, and I don't have time to explain, but Actually, so the Borel summation of the topological recursion partition function is written by the product of boundary functions because, you know, the previous, so for example, previous expression says that, so this one is Borel resembled to the boundary function, and by taking the exponential, so the linear combination becomes multiplication of the boundary functions. And actually, so the expression is essentially same as the tau function introduced by Tom for uncoupled case. Yeah. So actually, so we can relate topological recursion partition function BPS tau function after taking the Borel summation. So this was also written my paper with Omar. Yeah, I forgot to mention. So this is result with Omar Kidowai. So he is now in Birmingham. Okay, maybe this is almost end of my part, I think. Yeah, is there any questions so far?
Excuse me. So you mentioned this is also related to the DP environment.
DP environment. This one. Oh.
Yeah, at some point you mentioned. Yeah.
Yes. Yes.
And in which sense?
In which sense? Actually, at least maybe. So these examples are not considered in your paper. Maybe these are examples of amenable or unamenable. I forgot, but so for example, in A2 case, I can explain. So for example, so actually, so this is my next example, which is related to the 102, and it also appeared in the previous talk. And in the case, if we look at the Stokes graph, then we have 3 simple zeros, and from each 3 simple zeros are permanent like this. And it defines the triangulation of the surface like this by taking the generic trajectory in each Stokes region. So you obtain the triangulation of the hexagon. From this data, so you can attach some so-called Fourier category by putting some dots on the internal edges and draw some arrows in certain way. And actually, so this appears in the Tom's talk. So these orange dots are actually related to some closed cycle. So this is, for example, gamma A. This is gamma B. And these dots are related to such cycles. And this arrow is drawn when it is intersecting. And this is intersection number 1, so I draw 1. Then so omega counts the so-called stable object, which is to that. And to count the stable object, we have to fix the stability condition. And the stability condition is precisely given by the by the central charge. Okay, so depending on a parameter t and u, also maybe I have to mention. So actually, so saddle connection on a Stokes graph is actually related to some stable or BPS states in the language of Gaioto-Manaitsuke, for example. So yeah. Okay, so I'm not sure if I have to if I have to do more. Okay, so anyway, so these numbers are supposed to count such a BPS invariant, which is attached to some saddle connections in the Stokes.
So you can have a BPS quiver in this case.
This is a BPS quiver. It is called BPS quiver. And in hypergeometric cases, so since they are genus cell, so we don't have non-trivial intersection. So basically, so it's just a product of A1 quiver. Yeah. So in this sense, I think it's not, so actually nice category is not attached, I guess. I'm not sure. So yeah. Okay, but we can attach BPS invariant for such a degenerations following Gaioto-Manaitsuke and also Tom and Friedland. Then that definition works in describing the expression of the free energy. Okay, so this is basically the case of hypergeometric case equations. So the spectral curve is genus zero. So now I want to discuss the genus 1 spectral curve and relation to the Pandrov equation. So I think this should be related to the previous talk by Tom. But so maybe, so after coming here, so several people asked me, so what is the relationship between topological recursion and Tom's construction? But actually, I come here to learn it, I think.
Yeah, well, I don't know either, but yeah, listen.
Anyway, okay. Now, okay, so let us consider the elliptic spectral curve, or family of that. So actually, so T will be independent variable of the Pandrov equation. In this case, Pandrov 1 equation will appear. And the previous talk, so this was H. It is regarded as some other parameter, but actually, I use usual picture of Pandrov equations. I mean, so this is a function T. It varies appropriately so that we have some isomonodromy flow. So eventually, I want to give some get some isomonodromy flow. To obtain that, so from WKB point of view, so it is very natural to impose one of the period must be T independent. So in other words, we consider a family of elliptic curves with some constant A period. So that mu is some parameter which is independent of T, and by solving this relation locally, or implicit relation locally, so we obtain this family. At least this exists locally. Yeah. And
Does it not just mean you take T and nu as parameters instead of T and A?
yes. Yeah. T and nu as so this parameterization was used in embedded transform. Yes. And if you run the topological recursion and compute free energies, then we have this expression. Yeah. Okay. This T and U are appearing here, and so delta is a discriminant of this elliptic curve. And eta A and omega A are, maybe I'm not sure if I have to go, but just in case. So omega A is a period of x over y, and eta A is a period of yes.
And what is omega 0 2?
Omega 0 2 in this case is I need to erase. It's a basically pair function plus some correction. So this constant term is added to kill the A period of this omega 0 2. Yeah, yes. Yeah, actually, so this is G2 or Einstein E2 up to some normalization. Yeah. And since omega 0 2 is, it depends in this way. So the resulting topological recursion correlators and the free energy becomes a polynomial of this quantity. So you have some, with some appropriate degree. Okay. And so we can compute free energies, but I cannot write down the formula for F3 because it's too long. Anyway, okay, so the relation to the Pandrov equation is the following. So if we consider the free partition function by taking some exponential generating series of Fg, and it's a power series in H bar, and coefficients are function of T and nu, and I discrete transform it with respect to this parameter nu, and multiply some Fourier kernel. They are fully variable law. Then we have some family of anyway, so we have some formal power, not power series, but some formal series. And actually, so my claim is that so this is formal power series valued tau function of the Pandrov one. So it means that if we take the logarithmic derivative of this one, second type state solves the Pandrov equation, we see H bar.
So low is another marker. Low.
I will explain it later. Both nu and low will be related to the monodromy data.
Yeah, arbitrary.
Yes. And it is a second order equation, so we need some two independent integration constant, and this nu and low will be related. It's constant. And actually, these will be related to the Stokes multipliers for the isomodromy system, at least conjecturally. Okay. I have to say several things. So, for example, so this kind of discrete Fourier transform was already considered by Bertrand and Nicolas and Marinho, maybe. It's a non-perturbative partial function. And yeah, yes. And this construction, so I constructed in Pandore one case, but it is generalized to other cases by people here. Yes. So this is available for all Pandore equations. And actually, so this is some topological recursion version or analog of the formula of Oleg and Gamayun of Litopi. So they construct the power function of the Pandore 6 equation by discrete Fourier transform of the conformal block. And yeah, so actually, so this one should be related to the conformal block in that sense. But in irregular situation, in Pandore one case, for example, so the corresponding conformal block was not known until June, maybe. But very recently, so Pogosyan constructed or proposed some conjecture. So they proposed some irregular conformal block, which is related to this one, and check the series expansion agrees with the Pandore's asymptotic expansion.
Couple again, the C equals 1.
This is C equal 1, should be, yeah. Undefined or self-dual vector.
But they do for arbitrary.
Yeah. So Pogosyan, the construction is, yeah, they construct arbitrary as C. And C equal 1, they relate this expansion to the Pandore asymptotic. And also, actually, so the previous free energy is also related to the first part of my talk. So we can, maybe I should say, so to compare this result to, for example, CFT computation, so we have to change the order of the summation. So for example, so this one is defined by some H bar power series, but usually conformal blocks are defined by some large T or small T expansions, depending on the model. So to compare, so we have to develop some method to compare large T expansion of these free energies. And recently I discussed it with Nicola, Korea, and Oleg and Shira. And yeah, we could obtain this kind of result. So for appropriate choice of the A cycle, we can compute the large T expansion. And it is given by some convergent series expansion or with respect to this parameter. And for some reason, I'm looking at some large T expansion along the real negative axis. Anyway, so this is given by power series, and whose constant term precisely agrees with Weber's free energy. And actually, so this is related to the so-called conifold gap property. And higher order coefficients are also computed. And essentially, so this is rational number. And you can observe for this square root of 6, it's some annoying factor by rescaling of this capital lambda. So it is essentially the rational power series.
Okay. Question. The second sum is over L?
L, yes. Sorry.
Okay.
Oh, I made a mistake. So this should be L. So it's a power series expansion in capital lambda, a small lambda expansion. A small lambda expansion is, and also I have to put minus sign here. Sorry, I'm looking at the large T expansion. Yes, and also, so if once we have this kind of behavior, so actually we can compare this to some other computations by holomorphic anomaly. So actually, so from previous slides, so as we have seen, so this is written by some polynomial in this eta A over omega A. So it is essentially the Eisenstein E2. And also the T and U are basically E4 and E6. So it is quasi-modular up to this, for example. So discriminant, which is the Dedekind zeta function in this case. And it is polynomial in E2, and it is not it's satisfied the holomorphic anomaly equation. Okay? And for example, if we start from holomorphic anomaly equation, so we have to fix the ambiguous term, holomorphic ambiguity, by import some condition. And usually, so this condition was used to fix the ambiguity. And what I proved is, actually, so this, I start from topological recursion and derive this formula. So this says that, how should I say? So it is, anyway, so this gives some rigorous proof of the conifold gap property, at least in our example. So, so this should agree, and this agrees with, for example, Algeris Douglas partition function computed by Toyes group, and also so recently Alpha Grush and collaborators also compute this one by imposing this condition. So what so this says that this agrees with topological recursion. And so let me explain about the Gu-Marino conjecture. So Gu and Marino proposed some, before Gu and Marino, so many people proposed about the Borel summability or some Borel singularity on the topological string energy. And actually, so many people believe that the Borel singularity of the free energy is given by period of the Miller-Calabian. And in our setting, so it is given by some period of YDX. And from the previous holomorphic anomaly, so the Ricardo and collaborators tried to understand some non-perturbative structure of the solution of the holomorphic anomaly equation. Ricardo couldn't explain, but they put some transit answers and tried to solve the holomorphic anomaly equation in this transit setting. And previous conjecture implies that this transit action should be related to some period. But the competition was very hard, so we have to solve transit by term. So leading term should be related to the original perturbative free energy, but no perturbative one was difficult to compute. But so last year, maybe it was in November or December, Gu and Marino developed a method to compute this transit terms. And they obtained some closed expression of the transit formula, and also proposed a conjecture on the alien derivative. And for this X0 is the previous free energy, so perturbative one, which was discussed in the, for example, first part of my talk. And if this S, Borel singularity, is realized by B period, then the transit, alien derivative must look like this. It should involve some shift of the parameters. So this is a Gu-Marino's conjecture. And if we look at the A-cycle Borel singularity or alien derivative attached to that, the formula should be same as the perspective Schiappa's formula. So these are proposal of the Gu and Marino. So this came from the holomorphic anomaly analysis. And my next goal will be I will heuristically derive the same formula by analysis of the Pan-Louvet equation, and also using the relation between Pan-Louvet and topological recursion and isomonodromy, and also I will use some exact WKB philosophy.
May I ask you a question? So this formula works for, what is the genus of spectral curve in this?
I'm restricting my example, so genus one spectral curve. Yes, but they propose several conjectures on, not only for, they consider more general cases.
Based on the topological string?
Yes. Based on holomorphic anomaly.
Are they conjecturing the compact value?
Not in this paper, but in this year, maybe it was April. So Gu, Kashanipour, Krem, Marine proposed some conjectures. Yeah, and one for this formula is same. So this is their proposal, and so actually I haven't go through detail, but they propose. They also do some Borel-Pade approximation and try to check this in some examples. And here maybe I forgot to mention, so this parameter A plays a role of the Stokes constant, which cannot be fixed by transit answers. Right? So the transit analysis usually implies some almost the shape, but up to some normalization constant. And this will be related to the BPS invariant. Yeah, okay. So this is the formula which I want to derive from now. Okay, so to derive the formula, so I will use some isomonodromy deformation. The idea is very simple. So since Pan-Louvet equation is a flow or related to some isomonodromy deformation of the differential equation, so the corresponding Stokes data is some first integral. So we can use the Stokes data to relate the function in some different chambers. Or okay, anyway. Okay, so to use isomonodromy properties, so first I have to consider the so-called perturbative wave function, which appeared in Bertrand's talk yesterday. Yeah, so I just in my talk, I didn't define omega chain, but thanks to lecturers, so I can omit several definitions. In genus zero case, for example, in Aries example, so you have seen that it satisfies the Aries equation. But in genus one case, so we need some H-bar collection terms. And in this case, not only that, we also have to consider some partial differentiation term. And and we also need some H-bar corrections to the spectral curve. And actually, so you have seen this formula in the end of the talk. So this is basically P tilde, or part of that.
So when you say BPZ, you further inserted simplification.
Yes. Sorry, BPZ type. So maybe for Gaussian didn't discuss, but if we insert some degenerate insertion, then that may be related to this one. I haven't checked, but yeah. All right. Yeah. Okay, so yeah, we have this formula. And also, so this perturbative wave function satisfies nice property. So for example, if we consider the A-cycle formal or term-wise monodromy, so it is just very simple. But if we consider the B-cycle formal monodromy, then it is operator varied. So the parameter nu is shifted by integers. So this perturbative wave function has nice monodromy property, but one of them is operator varied. So to get some actual monodromy, it is natural to take the discrete Fourier transform. And actually, I borrowed the idea from CFT computation by Oleg and Korea and Teshner. And if we consider this discrete Fourier series, then B-cycle monodromy is just exponential law. So we have some, so this capital Y plus Y that have constant formal monodromy along A-cycle and B-cycle. So this can be some isomonodromic, some formal WKB type of function. And actually, so we can prove that this is a formal solution of the isomonodromic system attached to Pandore 1. So I don't have time to describe the isomonodromic system, but it is very similar to the previous Tom's equation.
Yeah, can I ask a stupid question? So normally when you do Pandore, you consider a cubic oscillator plus some apparent singularities?
Yep.
I don't see those here, but is that...
Will appear, yeah. Actually, so by taking the discrete Fourier transform, we have to remove this t derivative term to get ordinary differential equation. In the process, the apparent singularity appears. Sorry, I have to say more about technical details. Anyway, so yeah, your apparent singularity do appear from this. So, actually, so as I said, so this y plus minus have exponential of mu and rho as an A-cycle and B-cycle formal model. And in the WKB language, so these such as periods should be related to the Stokes data. And in WKB language, so they are called both symbols. Actually, so this, how should I say? For perturbative wave function, so the Borel symbol is operator varied, but after taking the discrete Fourier transform, so we can say so these two are Borel symbols. And if we apply the exact WKB computation of the Stokes data based on these Borel symbols, then we obtain the following explicit formula of the Stokes data. Actually, so in my paper in 2019, I also proposed some conjectural recipe of the computation of the Stokes data of the isomonodromy system. So the idea is like this. So idea one. So maybe I don't have time to explain about the Boros connection formula, but basically the Boros connection formula relates the analytic continuation of the WKB series to some integration or some formal analytic continuation on the spectral curve. So the consequently, the Stokes multiplier of the Borel-Lisandro WKB solutions are written by period, or its combination of the periods. And actually, so I apply the same philosophy to the previous isomonodromy wave function by assuming several things. So for example, so far the Borel summability of partition function Z is not known, for example, and also the Borel summability of this wave function is not known. So previous WKB Borel summability result is only available for ordinary differential equation. We have to develop some method. So anyway, so the Borel summability is a conjecture, but if we assume such things, then we can perform some explicit computation. And the Stokes data is written by appropriate combination of the both symbols by exact WKB philosophy. But this computation is available when the Stokes graph is saddle-free. So if saddle connection appears in middle figure, we cannot expect the Borel summability of the WKB solution because, as we have seen in the previous, first part, that such a saddle connection is related to some Borel singularities. So we cannot expect the Borel summability, but if we perturb the parameter by adding some imaginary part, then this saddle connection resolved and we obtain some saddle-free Stokes graph and apply the WKB computation of the Stokes data before and after this degeneration.
Why? When you say we cannot expect Borel summability, it's what? Of the series of DFGs?
Almost all three. So function shouldn't Borel summable.
So the perturbative partition function?
Yeah, perturbative one. Yes. Perturbative say is not Borel summable. Also, the I in my previous. So the perturbative wave function also doesn't. So anyways. So the saddle connection breaks the Borel summability for all several things. Anyway, so you read the compute the Stokes data, and then you can observe that, for example, this S0 are identical, but S minus 2 are not identical because of the. So here, S minus 2 is a Stokes multiplier from here to here. So here we have to cross two Stokes curves, so we have to consider some two periods. But here we have to know the only one here, so the Stokes multiplier looks different. This implies, philosophically, this should imply that before and after the degeneration, some tau function should jump in certain way. And the way of the jumping should be related, should realize some isomonodromy property. So if the tau function defined in this region and this region are identical, then they should have the same monodromy because Van der Waals equation or analytic continuation by T is isomonodromy flow. So we should have the same monodromy. So consequently, the previous parameter, nu and rho, must be related by the cluster transformation. So sorry, I'm talking very heuristic issues. But in fact, it is natural because, as I said, so this nu and rho play the role of the both symbol, and they are realized. So they are closely related to the Fock-Gonchar coordinate, and they are cluster variables. Okay. So anyway, so this should happen to get some isomonodromy. And then we can convert this relation to the other relation of the tau function. So if the tau function are roots, then as I said, so the Stokes data are identical. So we have to change the parameter nu, like this. And maybe I mentioned, but in this picture, for rho doesn't change, so we don't need to change the parameter rho, but we must change in this way. And actually, so if the Stokes data changes in this way, then it is natural to consider the prefactor like this. So it is a generating function of this monodromy simplex morphism. So you can see that. So if you take the logarithmic derivative of this guy by rho, then it will give this one. So it is a generating function. And actually, so this can be understood as some dependence on monodromy on a tau function. So actually, so original Jimbo-Miller Ueno tau function was defined by only looking at the T deformation. But if we can add the Jimbo-Miller Ueno one form and monodromy depending some one form. And this was discussed by Oleg and collaborators. Also, Beltra-Korotokin understood such a simple mutation or simple flip is related to some dialog or Rogers dialog, and it is closely related to the previous result. But if we, then the point is that so the perturbative energies or partition functions are Fourier component of the tau function, and so this one exponential 2 pi rho over h pi is a Fourier variable, and you can look at zero Fourier modes of the both sides. Then you recover the previous formula proposed by Gu and Marino in last year. Okay. So the previous formula looks very complicated, but it appears by looking at the zero Fourier mode So in other words, if we consider the discrete Fourier transform of Q-Marin's formula, then that will be the cluster transformation, or very simple formula at the level of the tau function. Okay. And also maybe I forgot to mention, so the right-hand side, Q-Marin's formula has a well-defined transit expansion by the Seiberg-Witten relation. So that, I should say, so the instant number is related to how many shifted from the original perturbative one. And as I said, so this recovers the Q-Marin's formula. And maybe you remember there was a Stokes constant in front of this formula. And actually, so this computation says that this is 1. And actually, so this 1 is nothing but the BPS invariant for the B cycle. And if you remember the formula which I proposed to you in the first part, so it's a jump formula of the Borel symbol. So the Borel symbol jumps in this kind of cluster transformation, and BPS invariant should appear here. And this is 1 in our case. And if you look at the cluster transformation here, omega should appear here. By taking log, omega should also appear here, and also here. And this omega directly appears in front of that. So in this sense, we can conclude that this constant is realized by BPS invariant for cycle. So this is basically main proposal of what I did with Marcos. Okay, so it's my last slide. So actually, so this is also, I expect that this is related to the Ricardo's computation of the Stokes multipliers. So for example, at some point he said that he introduced the so-called Stokes vectors and the coefficients are related to some theta values. He said that. And actually, so if we look at the Borel sum of this guy, for example, then as I said, or as I proposed in my in the collaboration with young friends, so this one will be the Barnes G function after taking the Borel summation, as we have seen in the first part. So this shift appearing in these instant terms will give some zeta values, because Barnes G function have the zeta values in a series expansion of nu equals 0. I believe that so this formula agrees with the formula by some manipulations, from rectangular framing to diagram framing and so on. So I haven't computed, but I believe so. And also, we assume too many things for Borel summability of partition function, convergence of discrete Fourier series, and so on. So we have to prove them rigorously. And recently, I'm also interested in many approaches, so relation between many approaches to compute the tau function. So originally, so like, so-called key formula use conformal block to describe the tau function, but later it is, or by AGT, so it is related to the Nekrasov type of partition function. And the topological recursion partition function is the third guy. So they should be related. But as I said, so this is H bar power series and this is large T or small T series, so we have to compare. And maybe I forgot to mention, sorry. So in collaboration with Oleg, so we developed some method to compute these numbers term by term recursively. And this also agrees with the large T expansion of the Panobel transcendence studied by many people. So this should be related to the irregular conformal block expansion. And we could derive it by purely from the definition of the topological recursion. Okay. So this is a final remark, and personally sorry, before the final remarks, I want to say this. So actually, so in the first part, I discussed some topological recursion and BPS invariant for differential hypergeometric equations. But I think it's also interesting to study similar relation for Q hypergeometric equations. Then in this case, maybe omega 01 should be log y d log x. And exponential network maybe plays some role. And finally, so the holomorphic anomaly implies some modular or Eisenstein series. So it plays a role of something in the Panobel equation. And Panobel equation is known as some generalization or some deformation of the elliptic functions. It has some nice arithmetic properties. So maybe there is some interesting arithmetic feature behind the Panobel equation, but nothing is known. So I think it's interesting. Okay. This is the end of my talk. Thank you for your attention.
Any questions? Yes. Can we do the same analysis for analysis?
I haven't, but at least the method I developed with Oleg and Yogo Hagan should be applicable to other cases. I haven't do it, but I hope to, if we choose appropriate cycle, maybe some class of combinatorial formula can be seen. But maybe from this topological recursion, obtaining closed formula is still challenging, but term by term maybe we can see. I haven't tried, but I hope so.
Can you say why the Seiberg-Witten relation gives a well-defined transeries?
So the transeries is basically the power series times the exponential of something. So actually, by our computation, so some higher order instanton terms are written by something times the exponential of our perturbative free energy shifted by k times h bar minus without shift. And so f new h bar starts from 1 over h bar squared. So if you look at the leading term of these, then you see f0 new minus kh bar. That's something you have to subtract. And by expanding this, so this is h bar, and by expanding this around h bar equals 0, so you have 1 over k and 0 mu, and so on. And this is nothing but the B cycle period by Seiberg-Witten relation. And k, so the number of shifts is related to the k instanton number. And this B cycle period must appear as a consequence of the area derivative because we are looking at the B cycle for reality in my last model. So as I said, maybe as I didn't say. So we are looking at the third connection along B cycle. So this B cycle period lies on the positive real axis because this is Stokes graph is defined by some vanishing local imaginary part. This implies B cycle period lies on the positive or negative real axis up to time, and we are looking at the area derivative. So it is natural to have this in front of the exponential.
Okay, thanks.
So maybe just a comment. So this form that the BPS invariant multiplies the dialog and the log. So this is also something that we worked out for the resolved conifold, just analytically. So there's no. So before sort of Marigny-Gould conjecture. So in fact, by relating it to Tom's Riemann-Hilbert problem, so we can prove it.
Any other questions? Otherwise, before thanking Koei.